Good afternoon, everyone. Just a prequel. I'm not going to be doing a really technical talk, so don't worry about it, even though we did work with Howden, but I'm here to talk more about high-level risk, air blast risk, some of the learnings in terms of what can be implemented on mining operations. These are all my own views, so again, it has nothing to do with the regulators or any of the sites we work with. Most of the examples that are in here, they're actually made with training Vensim models, so they're not related to any of the sites. So firstly, I'm going to talk about air blast risk in mining operations, why we worry about it, some of the things that have happened in the past. Again, there's a couple of incidents in there that some people may be familiar with, some people might have been involved with, so just keep that in mind. Then I'll be talking a bit about reactive versus proactive management, and then talking about some design examples and how we can improve designs and what impact that's going to have for your operation down the track. I'm of the opinion that air blasts, wind blasts, air rushes, whatever you want to call them, they're mining hazards in all underground mining operations. Not just cave mines, which is initially my background. Here in New South Wales, we got 2 design guidelines. I know they're getting updated at the moment, but they are defining an air blast as a rapid displacement of large quantities of air, often under pressure in a constrained underground environment. Now, every underground environment is constrained, and so as a result, we're going to have an air blast risk in any underground operation. From a risk point of view, any operation that has unsupported ground, it should be treated as a principal hazard. As long as you don't have any support in that ground, you're going to have potentially an issue with air blasts. So obviously in sublevel and block caves, as we progress to caves, it is a principal hazard, and that's where it mostly gets managed. The wind blasting from gophs in coal mines, they've led to some really severe incidents as well. So the coal mines are trying to stay on top of it, but the area where we probably have the least amount of risk assessments and hazard analysis is unsupported shafts, raises and ore passes. And I would argue most underground mines will have one of those. So I think everyone should have a look at that as a principal hazard for their mine. And it is a secondary hazard for all other operations. So as it says in that definition from the regulator, fall of ground. Now, we generally treat ground and strata failure as a principal hazard, but quite often we're trying to prevent that, but we don't necessarily always look at the consequence. If we do get a ground and strata failure, what happens after? So putting some mitigating controls in and determining the air blast risk of that. Now, I'm going through a couple of examples here. The first one is fairly old, from 1895, and I actually pulled that off that disaster timeline from the regulator. And I find it really interesting when I read that. So back then, there was an area in the Broken Hill silver mine that they had issues with ground, and on that particular day, the shift boss was saying, I'm not sure about what's happening here, I think we might have a potential fall of ground. So he identified the primary hazard of there might be a fall of ground, pulled all his people back, and failed to recognise the hazard of what happens when that ground falls. And as a result, 8 miners got killed that day, and a 9th miner died the day after in hospital. And the mine manager afterwards said he thought they had that mine so well timbered that they couldn't have any creep of ground. So again, the perception of what we're doing is safe to what potentially can happen. And that's a clip from the South Australian Chronicle from the time, which you can also find on the regulator website. The next ones are from the Newcastle coalfields. Those of you who work and have worked in those coal fields would know in the 70s and 80s there's been quite a lot of incidents of wind blasts, and as a result of that there was actually an ACARP project implemented that Dr. Farlow and Dr. Charmer from the University of New South Wales had a lot of involvement in. There was another ACARP project that happened as a result of the Mara 4 incidents up in Queensland, which, even though unconclusive, a lot of people believe the initial windfall, the initial air blast when the Gove collapsed actually then started an explosion that led to the explosion of the mine. And there was another one at Endeavour Colliery which was of similar incident. So in the coal industry, a lot of focus is on the explosions, but a lot of these explosions actually get triggered by a Gove fall that results in an air blast, stirs up coal dust, and then creates the conditions for a coal explosion. And the last one there, obviously North Parks. This is the one I first got involved in I came across to Australia as a student in 2006, and I was quite amazed by, you look at it, and 2020 is always good, you sort of look at it and go, well, you got this massive air gap of how could that happen, but then you look at leading up to it and how events took place. Again, it comes to this, things change over time, management of change, and identifying the risks that as a result change with that, and that's something we really need to have a look at. So what usually happens when we do air blast assessments? Well, somewhere in the pre-feasibility and the feasibility study, someone starts with doing a project risk assessment and has anything like that, and air blasts get identified as a risk. In caving operations, most other places not necessarily, and someone goes, yep, that starts being an issue once we start operating. So we're going, well, that's, undercutting, production startup. Same for a stoping operation, we start production, okay, we have some instability in that particular area. Someone needs to have a look at it at some point. All resources constrained, so what do? Well, someone gets a task assigned and has a 2-3 year lead time, do it before we start production. And as a result of that, well, shafts usually don't get identified at all. When someone then goes, we need to have a look at this air blast risk, all the infrastructure's already in place. So we're sitting there and going, yep, we know there's a risk, we know we need to do something about it, and we keep leaving it because we're obviously resources constrained and it's not an issue at this stage, and we leave it till we can't ignore it anymore. And then we go there and we're like, how are we managing this risk? And at that stage, if we do identify engineering controls, we go, that costs a lot of money, that wasn't no budget. And so we either have to get out of budget money or we have to put in administrative controls. So having stolen Anthony's slide, we're down in that really lower bottom of the safety triangle and trying to retrofit controls to risk we've already put in place. So what should we be doing? Well, a lot of sites have technical guidelines in terms of how they do their mine designs. Instead of waiting for your project risk assessments, put air blast guidelines into your design guidelines for your engineers that do your planning and that do your mine designs, and make it part of your design process. And a lot of, as I go through the examples, you'll see that there's some very easy things you can put into the mine designs that dramatically lower your air blast risks. Shaft stability assessments. Everyone does them, loves them. You drill a cover hole and then you get that report back and it says, yep, there's zones of weaknesses. Well, okay, so are we happy with the size of the zones of weakness, what it is? But if that shaft fails, what will actually happen? Like, what is the risk to the mine of a failure at that particular spot? Startup of a sublevel cave. How big is the void? Does the void have to be before we reach hydraulic radius? So the hydraulic radius is at that stage caving sustains itself, and so until you reach that, you're basically creating a large stope, and you're leaving some material behind that acts as a blanket. The bigger the area is that you have to create before it caves itself, the larger that void is going to be, and the less of the material you're mining initially you should be extracting, because you need to leave the rest as a safety. Same thing in stopes. You get a geotech assessment of your rock mass, and that says, oh, you can do a 20 by 25 metre stope. And then that's your critical span, then you're starting to have issues. Well, okay, 20 by 25 metres, if that does fail, is that going to be an issue for the surrounding mine network? Or is it better that we reduce the size slightly, and so your factor of safety goes up a little bit? Also, the impact of a failure is going to be a lot lower. And then in the coal industry, like, you have massive sandstone formation overlaying coal seams. Will it fail continuously? Will it fail in slabs? I worked in a coal mine over in Germany, and for us it was the footwall that failed in slabs, and it started creating these massive seismic events, and it actually expelled air from failings in the footwalls and creating similar issues from what you get here in some of the coal mines here. Do we need to put preconditioning in the budget? If the geotechs say that hanging wall is stable, well, then we need to put it in our production plan that we might have to do remedial work, and at what point do we have to do it? When do we cross that threshold from the failure when it fails, it is safe for my operators, to I really need to break this roof up, because if I don't and it fails, it has the potential to actually really injure someone or even kill someone. For block caves, when the block cave fails, does the air all come out of one or two airways, or can I actually distribute the air around the mine? And so what we're trying to do is we're trying to get away from the administrative control and move up the safety cross into your substitution, your engineering controls, and your elimination, and you're trying to do it as part of the design. So in the end, it doesn't actually necessarily cost you much more, but you're achieving much better outcomes. So what's the risk? There's two stopes, roughly. They're exactly the same volume, 70,000 cubic metres. Which one is safer? Left, right? Airblast and air expulsion from a stope is only a function of height. It doesn't matter what area you have that you're undercutting, you will expel based on height. So if you have a coal seam that's only 5 metres high, all the air is going to come out in roughly a second. But your coal seam is generally, longwall is generally 200 metres long, and however deep your gove is, so you're going to look at a lot bigger area than a stope that's, say, 20 metres wide and 20 metres long. So from a risk point of view, you want higher excavations that have a smaller footprint. So if you can do that, that helps a lot. And no, I'm not saying redesign everything. It's just something to keep in mind when you are designing your infrastructure, your stopes and all of that is what is the potential outcome if you do have an issue. So you're looking at a 41% maximum reduction in air velocity coming out of the base of that stope just by having a different geometry. And that makes a big difference in your mine network where the air needs to get dispelled from its source to the surface. So shaft failures, as an example, I was just talking about it before. You get a stability plot like that, which I've just pulled out of paper. In this instance, you got an area down the base that's fairly low stability, and you have a look at that and you're like, no, I don't know about that. Got a couple of areas further up. So what you can do is you do an assessment of the air blast risk. You say, okay, if I have a failure 100 metres up, I'm doing a 3 metre shaft, and these two aren't linked, they're different models, so don't take it too much in context, it's just more to show a point. Out of the base of the shaft, your maximum air velocity coming out is about 13 metres a second. If I know I have a failure that's 300 metres up, same shaft, same everything, your maximum velocity coming out of the base has now gone up to 24 metres a second. So where your zones of weaknesses are has a dramatic impact on the outcome if that shaft fails. And then you might want to go, well, what about if we're doing a larger shaft and I only have issues down the base? Well, going from a 3 to a 4.5 metre shaft with a 100 metre high failure, you basically have the same air blast risk as a smaller shaft 300 metres up, because it's all about the height. Your volume comes out at the same time, so the larger that shaft is, if the failure height stays the same, the bigger your risk. Which, the good thing about that is generally the ground support, we can do better in the top half of the shaft than we can do in the bottom half, especially with those long shafts that are 500-600 metres long. So when you're looking at ground support in shafts and raises and everything, you probably want to do that top half of the shaft more from an air blast risk anyway. The other thing with shaft failures is, especially intake and exhaust shafts, all passes are slightly different because they might have material in the base. They're generally open at the base, so there's nothing that prevents the air from coming out. And because you're having the downward force of the falling material, the resistance that the mine network offers is generally negligible. So whatever gets displaced comes out the base, and you're going to have to deal with it in the mine network. So it's actually a really simple calculation. Year 7 high school physics, free fall, you drop an object and it accelerates with gravity. And so just as an example, so you look at the left-hand side is the time. So, and I mean, you guys know what height shafts you got on your mine side, and then how quickly that air in those shafts gets displaced and how quickly the volume coming out the base of that shaft is building up. And then you have to have a look, well, what drives do I have available at the base of the shaft? Like you look at that nearly 500 metre shaft there, it goes up to nearly 1,500 cubic metres per second. If you have a 30 square metre drive at the base, you're talking about 50 metres a second of air coming out that bottom. Normally, when we do air blast assessments for the caving industry, we say we do not want to go above 20 metres a second of air velocity, because above that, you get projectiles that can cause a serious injury to your workers. And also the pressure waves associated with that can start causing quite significant injuries to lungs and similar. So some of those shafts, even though they're more localised because the total air volume is a lot less, can have a severe impact on your workers in the vicinities. So something to consider when you're doing shaft designs. This is an SLC example, but it works the same for a stoping mine. Exhaust versus intake regulated levels. Now, exhaust regulated, we all love them. You got an open access going on to the level. You don't have to deal with doors. They're easier to manage. Usually you put your regulators in early in your exhaust, which also means most people make them blast proof. Which in the event of a roof fall that causes an air blast makes it hard, because what happens is all your air is going to come out that central access, and that's where all your people are. If you compare that to an intake regulated, where you have, at that central axis, you have a door or double door, and you're running your vent across that door. First of all, you use less air, which I do ventilation a lot, so I like doing that. But then in the event of a failure, you're actually venting all your air straight into your exhaust. So your main decline, where people travel up and down your access ways and everything like that, is actually much more protected. So the tailings dam guys use a concept called personnel at risk, like they were talking about today as well. When you're looking at air blast risk, you want to look at your personnel at risk. How can you divert air into areas where there's less personnel? So in this instance, you're diverting the air blast into your exhaust system, which generally the only people going in there are vent officers, sometimes maintenance personnel, but it is generally a controlled area, so you can have a look at who's going in there, why are they going in there, how often are they going in there. Whereas if it's unregulated and you haven't really thought about it, you're putting all your production personnel at risk that are down in the mine for 20 hours a day. The other thing we've done with SLCs is designated air paths. So as you mine out your top level, instead of closing it off completely, like a lot of times we might close these extraction drives and put plugs on them. In this instance, we actually close off your access to the levels, but leave it open to the exhaust. And that's what I just said about personnel at risk, removing the risk from your operators. Because now these guys on the level below where they're actually operating are much more protected from the air blast risk than they would be otherwise. Because if you close this off, you had an air blast, all the air has to go through that muck pole and come out where your operators are. So it's about diverting people away from the risk. Shrinkage stoping. Now, this mine is a bit, it had a few issues because it's a vent model, so it doesn't have an exhaust in here at all at this stage because it was an operation that was actually open to the pit on the other side, but it's just to illustrate a problem. So you're operating stopes in here, you got a failure in your crown pillar, and all the air gets pushed out your one way, and it's your only access into that level, where quite often there's no parking in here. People might park over here, they go in there on foot, and you're exposing people to a hazard. And again, most of the time it's probably fine. It's when you have issues with your hanging wall and you're concerned about hanging wall failures, you probably should have a look at designs like this and figure out, well, is what we're doing actually okay? The other thing that this one illustrates fairly well is your escapeways. Because they're one of the shortest connections to surface, they're actually one of the primary paths that air takes when you have a failure. It always tries to take the shortest route. In this instance, they actually have doors in front of those, so it's not quite as bad as it could be. But that's just something to keep in mind as well. So what we do, well, we put the exhaust into this area, and again, we're creating a designated path for the air straight to the exhaust, and whether it goes straight to surface or just somewhere into a return airway. But if you look at the colours here, you now have a lot less risk where you got your people and where your people move around. The other thing with this one is, well, you look at the speeds there, and I was saying before 20 metres a second, well, this simulation assumed a certain extraction ratio. I now have a lot more leeway to go up with that, so I could potentially bring forward production from a higher level, which then has a positive impact on your plan. And in most situations, you would have to put that raise in anyway. It's just by moving the raise, you're actually reducing the risk, which then means you can change your production plan to create a more positive outcome. I'm actually getting through way too quick, but so airblast risk assessments is all about understanding the outcome. It's not about determining the likelihood of failure. It's about if you have an airblast, what does it look like? Where are the concerns in your mind? Where are the areas that we might be able to change something in the mine design to then reduce the risk that we have to address? Should be done early, so you can do it as part of your normal approval cycles, as part of your normal project cycles, and then work from there. And it actually creates value for the company, and it means that you have to do a lot less work. Changes to design, that's one of my favourites. Like, we give assessments to the operations, and then someone changes the design, and all these assessments are based on assumptions. So if you change the mine design after you've done an assessment, you need to go back and have a look, does that significantly impact the assessment that we have, and do we need to change the guidelines? They should be part of your design checklist. So if you do an AFC approval, has someone looked at this? Like, give it to your vent engineer. They can be done pretty easily, like you don't need to do complicated stuff, or you can tell your vent engineer, put a fixed flow in, just push air through and see where are the areas of highest velocity within the mine if we have an issue in that particular area, and it shows up pretty quickly. It doesn't have to be an accurate assessment, but you will see where your areas of highest concern are. If they're in the return airways, you know what, you're probably all right, you don't have to worry about it. But if they're in your main travel ways, you want to have a closer look at what's actually happening. So what we're trying to do is get away from the reactive model to the proactive model, and trying to work in early to manage the risk before it becomes all about administrative controls and telling people you can't go there or you have to stay in your vehicles and all that sort of things. Now, I understand it's hard when you don't have brownfield sites, but yeah, when you have greenfield operations and projects, there's a lot of things you can do early, and that will help you. Thank you.